Hello friends, welcome to my channel. We are going to discuss about the principle of mathematical induction in this video. So, first of all, we are going to describe about inductive set. And what is inductive set? We are now going to define it. So, a subset of real number is called an inductive set if it has the following two properties. First, the number 1 must be in the set, and for every x in the set, the number x plus 1 is also in the set. So, we write the definition of let S be the subset of R and S is non-empty and S is called an inductive set. An inductive set of R if it has following two properties. Two properties. First, 1 must be in the S, that is 1 is in the set, and second, x belongs to S implies x plus 1 is also in the set. This means that if x is the member of set, then x plus 1 is also the member of the set. So the set having these two properties is called the inductive set of real number or inductive set of R. What is the properties are? 1 must be in the set S, and if x is in S, then x plus 1 is also must be in the set S. So again we are moving forward on another step. We have the smallest inductive subset of R is a smallest inductive subset of R is called the set of positive integer. It's called the set of positive integer, that is n. Thus n is the set of natural number or the set of positive integers are the smallest inductive set of real numbers. So a real number is called a positive integer if belong to every inductive set, or in other words, a real number is called a positive integer if it belongs to every inductive set. Every inductive set. inductive set. So we have set theoretic definition of natural number or positive integer is, we can write in other way. If consider the set t equals to s in the is the subset of R, T is the subset of all the subsets of real numbers, such that S is a inductive set. S is inductive. This is the set. So intersection of T is called the set of positive integers. So this is the smallest inductive set of R, since this is the intersection of all the inductive sets. So we have defined the inductive set, and we have also shown that the natural number is the smallest inductive set of real numbers. So again we are going to define an important property of set of natural numbers. This property is called the well ordering principle. And what is the well ordering principle? Is well ordering principle of natural numbers. Of natural numbers or subset of natural numbers. What is the well ordering principle? Well ordering principle is the every subset of set of positive integer has least element. Every subset of set of positive integer has a least element. Every subset of set of positive integers, every non-empty subset of set of positive integers has least element. In other way, equivalently, we can write it equivalently. If S is the subset of natural number, S is non-empty, then there exists M in S such that M is less than or equal to X for every X in S. This is called the well ordering principle, and M is called the smallest element of S. M is called the smallest element of set S, and we say that S is well ordered set. So what is well ordering principle is, once again, every non-empty subset of set of positive integers has least element. So equivalently, if S is the subset of natural numbers and S is non-empty, then there exists an element M in S such that M is less than or equal to X for every X in S. Again, we are going to discuss about the principle of mathematical induction. Principle of mathematical induction is, let Pn, where n is the natural number, be a mathematical statement having following properties. The first one is called basis. Basis is P1 is true. P1 is true. That is Pn is true for n equals to 1. For n equals to 1, Pn is true. Again, we have the inductive step. And what is the inductive step is? Second, inductive step. Inductive step. Inductive step is Pk. If Pk is true, then Pk plus 1 is also true. Then Pn, then statement Pn is true for all natural numbers. This is called the principle of mathematical induction. So the statement must be true for n equals to 1 if the statement is true for n equals to 1, and if a statement is true for n equals to k, and this implies that a statement is also true for n equals to k plus 1, then we say that a statement is true for every natural number. So we are going to prove this property. We prove this theorem by method of contradiction. So we are going to prove this statement. So proof of principle of mathematical induction. So consider the set T is the subset of all natural number for which Pn is not true. So that is T claim we have claimed that T is empty. Proof. If possible, the proof is by method of contradiction. The proof is by method of contradiction. If possible, assume that T is non-empty. T is non-empty, and we have T is the subset of natural numbers. So by T have well ordering property. So by well ordering principle, T has a least element. Say M. So M cannot be equals to 1 since P1 is true. P1 is true, so therefore M cannot be equals to 1 because M is the element of T. Therefore M must be greater than 1. So, and Pm is not true. Since M is the least element, therefore M minus 1 is not in T, and M minus 1, therefore M minus 1, P of M minus 1 must be true. Pm minus 1 must be true. Therefore, we have the definition that by above definition, Pm minus 1 plus 1 must be true, and this becomes Pm must be true, and this implies that M is not the element of T, but we have, this is a contradiction, that M is the least element of T, therefore this is contradiction. So our assumption is wrong. So T is empty, therefore T is empty. So Pn is true for all n. Thus we have proved our theorem. Thus we have proved the principle of mathematical induction. Again we are